All right, I guess we'll get started. So it's the first seminar of the quarter, and we're very happy to have Simon Catterall from Syracuse visiting us via KITP, and he'll tell us about lattice fermions and anomalies. So, take it away.
Yeah, it's very nice to visit here. It's been very pleasant so far, and very interesting discussions. So I'm going to tell you something today about what I consider a kind of new approach to an old problem, the problem of formulating chiral lattice fermions. And so you'll be able to evaluate by the end of the talk, how far along that path we may be. And so we'll see. The problem isn't solved yet, but this seems kind of interesting, and it's already gotten around several problems that I would have expected to have accounted by now. So this is the plan for the talk. I'll tell you a little bit of a very, very brief overview of what some of the traditional difficulties with formulating chiral lattice fermions. I'll then sort of conclude from that maybe this is never going to work well for fundamental reasons. And then we'll sort of take a side, we'll go off in a slightly different direction and talk about a different type of lattice fermion. I say newish because in fact it's actually very old. These Dirac fermions were actually proposed around the same time as the original Dirac proposal for the electron back in 1927 by Landau. Or they should be called Landau scalar fermions, and Dirac shouldn't be a part of it at all. But anyway, they're a type of fermion you can write down in the continuum. In flat space, they look very similar to multiples of Dirac fermion, but in curved space, they behave differently. And that's where all the interest lies as well. And they also behave differently in the context of lattice discretization. So it turns out that these things can be discretized in a way which preserves not only the analog of chiral symmetry, but it even preserves the anomaly structure. So I can do the calculation on the lattice or in the continuum and get exactly the same answer. Right? So that control over the lattice symmetries and the anomaly structure is what's important for sort of navigating this sort of path towards a potential resolution of the chiral fermion problem. So I can construct models using these scalar Dirac fermions that, at least in the naive continuum limit, look like chiral fermion theories. In fact, you'll see they look like them. They give very specific chiral fermion theories, for example. So Patti-Salam emerges very naturally from these constructions. But of course, that's not enough. We have to do the naive continuum limit is not enough. And so I'll make some comments about what's needed to really try to make a chiral lattice gates theory out of these things in the end. So this is some recent papers that are relevant to this. So frequently. All right, and just to give a shout out to my student, Anab, who's been involved in several of these efforts over the last few years. Okay, so it's, chiral gates theories underpin most of what we understand in elementary particle physics. It's the mathematical description that we need, of course, for the standard model. And so it's a very successful perturbative formalism, but of course it's, depending on your perspective, it's either annoying or embarrassing that we actually really don't have a non-perturbative formulation of what we mean by a chiral gates theory. All right, and so it's been a long-standard problem for the lattice to come up with one. There are various theorems. The main one is Nielsen-Ninomiya that says that basically this is a very hard and possibly impossible task, because if you can, this was shown in the early 80s, that any local Hermitian chirally invariant lattice action you write down will have equal numbers of left and right-handed fermions in it. And this is related to the phenomenon you may have heard of called fermion doubling. And the usual physical argument that's invoked at that point to sort of explain why this is necessarily always going to be the case is because no lattice theory can have an anomaly, and so there must be equal numbers of left and right-handed fermions to cancel out the anomaly, right? So as you'll see later on, this is actually wrong. This folklore is not correct. There are examples of lattice theories which have exact anomalies with a finite number of degrees of freedom. And so we'll talk about them in the context of Dirac fermions in a little while.
I assume the theorem itself is, strictly speaking, correct.
The theorem is correct. And in fact, we'll be avoiding it in various ways, as you'll see. Right. And this is it's a statement about the quadratic fermion action as well. So there are various other provisos, but there's nothing wrong with the theorem. The folk theorem is this one, that lattice theories don't involve anomalies, or rather kind of resolve anomalies. Sorry. So this, this was realized very early on in the 80s. The most successful effort to try to get around it go under the name of domain wall fermions or overlap fermions or Ginzburg-Wilson fermions. And they do this basically by modifying gamma 5 and the Dirac operator on the lattice in such a way that, in fact, they become, in some sense, non-local. Right? So these were proposed by Kaplan, Neuberger, Lucia, people like that. Is that my problem?
You may need to change that, maybe take a minute to,
Yeah, that's kind of annoying. Let's see.
yeah, there's
Is it
some,
me or is it it?
no, it's probably
Is the screen going dark?
Huh?
Is the screen going
No,
dark?
my screen is
Oh.
fine. It's just not mirroring properly.
oh,
Yeah. Oh, well, actually, let's just see. Let's just have a look at the settings.
that's okay.
It's not terrible. I just hate hitting it.
Yeah,
May not be worth running about.
I don't know, just,
Let's just do it. I'll just hit things more frequently.
okay.
All right, so these were proposed in the 90s, and at first people were kind of optimistic that this would be a solution to this problem. Because these operators are basically non-local, you don't immediately fall prey to the Nielsen-Ninomiya theorem. And in fact, in the case of vector-like theories like QCD, they work extremely well. You have good control over the chiral properties of the theory. You can even generate the anomaly, the normal ABJ anomaly, from the anomalous variation of the fermion measure, the lattice fermion measure, just like you would do in the continuum a la Fujikawa, right? So that's nice. Unfortunately, in the chiral case, they still suffer from a problem. It turns out the fermion measure is in general ill-defined, and I'll show you what I mean by that in just a second, because of the contribution of non-perturbative configurations. So still there's a problem here in the end, even for using these rather sophisticated formulations that I won't have to get into in any detail here. So let's go and see where the problem really lies. So if I write a path interval down, and I'm implicitly on a lattice here, so these are gauge links, and this is a finite integration measure, so only a finite number of fermions in the game. I take something like the Dirac action. This is some lattice Dirac operator. We won't go into the details, but it contains within it these projectors. So so it's just like how we do it in the continuum. I put projectors onto the Weyl fields left and right, and sandwich the Dirac operator by that. Right. So this curly D this involves this funny overlap operator. All right. Just trying to make sure it's not asleep. Sandwich between these projectors. And the difference from the continuum is that while P plus is the usual chiral projector, this P hat guy involves gamma 5 hat, which is this modified gamma 5 operator. So again, I don't need to tell you what it is, but it's non-locally determined by the gauge field on the lattice, right? So this curly D thing is some sort of non-normal complex matrix that maps you from right-handed fermions to left-handed fermions, for example. And one of the immediate things that strikes you is not only is it not diagonalizable because it's not in general normal, it's not even square in most cases. So if I have managed to construct some instanton background on the lattice, right, using there's an extra, say, left-handed zero mode floating around, right? That means this matrix, which you've realized in concrete terms on the lattice, is actually a rectangular matrix. So it's certainly not diagonalizable. And so what you know from your undergraduate, applied math class or linear algebra class is the only thing you can always do with a complex matrix is to decompose it using singular value decomposition. So I can always write this operator as in terms of two unitary matrices and a matrix, a diagonal rectangular matrix of singular values. All right, so those singular values are just gotten by solving d dagger d on some vector equals sigma squared. And so what goes into the elements of this capital sigma are just these singular values, which are real positive definite. All right, but these matrices A and B don't even have to be the same size. I mean, generally, it won't be the same size if you have some sort of topological instanton-like background. Right? So having done that SVD, though, you can imagine changing variables in the path integral, having decomposed D in this way, to try to do the fermion integration and come up with the effective action for the gauge field. Right, so I can imagine doing that. So I can, for example, introduce a new fermion, which is B dagger on psi, similarly something for involving psi bar minus, and integrate out those fields. And so when I do that, there's a Jacobian that comes in, and it just involves the determinant of these two matrices. These are unitary matrices. all right? And the product of the singular values, which you can just recognize as just this object here. So this is real positive definite, but in general, these guys bring in a phase, which depends on the background gauge field configuration. All right. So the first thing you would say is, if I want gauge invariance to be true, that it must be true that this phase is gauge invariant. And if you make that requirement, you get the usual perturbative anomaly cancellation condition, right? But things are actually worse than that in general, because I'm just going to keep touching. I don't know what the mess is right here, I'm sure we don't lose it. These matrices A and B are not unique. So SVD is not a unique decomposition. You can take the columns of A and B, which are bases in these two vector spaces, the left-handed space and the right-handed space. I can also multiply them all individually by different phases. I'm allowed to do that in the SVD. Now, in general, that changes these determinants because I'm changing the determinant of the matrix. It turns out to be okay if I don't have zero modes, because the phase of B, if this is the kth column of B, is related to the phase of A, and these determinants come in conjugate ways. So if I make a phase transformation on a column of B, it must be accompanied by the equivalent one on A, and so those phases cancel out. But you see the problem is, if this is rectangular and there are zero eigenvalues, there are zero modes of B, there are no compensating phases associated with A. And so in general, these product of determinants has an unresolved ambiguity associated with those zero modes. So this is the so-called fermion measure problem. This was pointed out by Lucia in the late 90s. And in the abelian case, there are some ways to resolve this problem, but in the non-abelian case, there are no non-perturbative solutions to this problem. Right? So this alpha, this phase in general, is non-local. It might be gauge invariant, but it's in principle, I think it's ill-defined. I can give it to two different graduate students and they can come back with two different answers. And those answers depend on the background gauge field configuration. So this is really where the problem of formulating the chiral fermions lies. And this is really a problem in the continuum too. It's just that in this case, we have concrete matrices that you look at, which come from your lattice regularization of the problem. And so it's really in your face. You have just ambiguities in the phase of your basis vectors. And so people have tried to fix this by building what are called mirror models, where they try to build you start from a vector-like theory which doesn't have this problem, and then gap out some of the states, put them up to the cutoff, and get left with a light sector. That approach so far has also failed, although I don't think it's impossible. People believe that a strategy might still work.
Can you comment more on what you said about it's also a problem in the continuum?
Well, formally it's a problem. It's just that these measures are harder to define in the continuum.
What happened? Can you see anything in dimensional regularization?
I don't know. Maybe you could tell me.
Well, there is a
It's
lot.
not a perturbative thing, so you're not going to see it unless you have a instanton-like background. So it would be something like that. So I don't know whether people have seen it there, but this is how I understand it in the lattice language. It's really just an ambiguity in what you mean by the partition function at all. And it's there not perturbative because it's only those configurations where this B can develop zero modes, for example.
I mean, there's certainly a lot of chaos in gamma 5 and perturbative, but that's probably a different set of chaos.
Right. I would say this is beyond perturbation theory.
Okay.
This is a problem of just in the formulation, and it hits you in the face when you're constructing a lattice model because everything is finite, right? Everything is just some finite matrix, and you just have an ambiguity in what you even mean by the path integral anymore. And so we'll see. This is the heart of why there's really a problem. And even if you have a good regularization, like Ginsburg-Wilson, you still face this problem. This is what Lucia identified a long time ago. All right. So you can ask, what can I do in this situation? If I take some sort of naive approach, then this Nielsen-Niemeyer theorem kills me. If I use something like an overlap operator, this thing I haven't given you explicitly, but that's the best. That's essentially the heart of the previous argument. I can build a theory with an exact chiral symmetry, so the lattice action is invariant under a chiral symmetry. But then this gauge field dependence of this projector leads to this non-local phase ambiguity in the measure. And it's not clear how to resolve that at all. So one thing you could try to do is to build a theory with no ambiguity in measure by starting in a vector-like theory and gapping out states. That is a perfectly good strategy. That's not actually, it has been tried and has so far not been successful. What I want to talk about now is to take a completely different run at the thing. So I want, instead of talking about gamma 5.
What are the words not successful? Do you mean
It means
practically not successful?
So typically what happens is you start with a vector-like theory with the symmetries you want, and say you want to construct something with just left-handed fields.
Yeah.
You try to design interactions that only target the right-handed fermions and push them up to some cutoff, so that the low-energy effective theory is just chiral.
And what
Making that work without those two sectors talking to each other is very difficult. That's the short answer. Not necessarily impossible. There's no theorem that tells you can't do it. Eric Poppins and people worked on this for many years, Joel Gee. And they were not successful, but there was no, there's no theorem that tells you it can't be done. And in fact, our motivation originally was to do something like this in the context of these scalar-Dirac fermions too. And it may still be a strategy that we need at some level. To make that work at all, you have to make sure you cancel off all the Toft anomalies in the system. Otherwise, it's guaranteed to fail. And so that will be part of the story here. So we will kind of revisit some of this. Sorry. As we go along. All right. So I'm going to stop this at this point and say, well, this hasn't worked terribly well. Can we do something different? Is there a different approach? So I want to revisit something. So as I say, it's sort of newish to most people in lattice too, but it's not new to everybody. It goes back to the earliest days of lattice gauge theory and even beyond that. Right. So I'm going to, instead of talking about Dirac fermions and gamma 5, I'm going to talk about Kähler-Dirac fermions and a sort of analog of gamma 5. And we'll just see how close we see how much you can push the same analysis through for Kähler-Dirac and see how close you can come to the original chiral problem. So these things have a twisted chiral symmetry. So I have to tell you what that is in a moment. But the key thing about that twisted chiral symmetry is it can be maintained exactly under discretization without invoking non-local gamma 5s. So the operator that works in the continuum works directly on the lattice. That's the first point, without any fermion doubling. So that's already an improvement over gamma 5, right? And over the usual problem. Not only that, but not only does the symmetry survive, but the anomaly associated with that symmetry, it has an anomaly, like the ABJ anomaly, but it survives on the lattice. You can compute it exactly on the lattice. I'll show you how to do that. It's much easier than doing it in the continuum, in fact. If you cancel out a related Toft anomaly associated with that, the residual symmetry, the non-anomalous symmetry, you'll see that the number of fermions in the theory has to be a multiple of 16 in 4 dimensions, 3 plus 1. So these special numbers, these multiples of 16 are known in the context of topological superconductors. So people have already done analysis about essentially, we're working with Weyl fermions in even dimensions and cancelling out certain time reversal-like anomalies in those dimensions, and they find the same magic numbers of fermions. So they come out of this analysis too, actually. So these are, or sometimes, it's really annoying. Comes back here instantly, but not there. I think it is me. So we'll see this as we go along. And if I take the minimal anomaly-free Kähler-Dirac model I can construct this way, it turns out it's Patti-Salat. So the lattice maybe is smarter than you think. Actually knows how to construct at least a subclass of chiral fermion theories, chiral gauge theories, maybe. So when I say it gives you Patti-Salat, it gives you the matter representations and the global symmetries of Patti-Salat. Those symmetries have to be gauged, and that's where the difficulty still lies. Some of them anyway. So what is this Kähler-Dirac equation? So this is the original paper, came out in March 27, a couple of months after Dirac's paper. It's only occurs in it's a flat space theory, and it's written in components. So as you'll see in a moment, it's best the right Kähler-Dirac theory in terms of modern differential geometry, but it was written in component form by Landau and his student. This is a quote from the paper. So this actually came out in preprint form before Dirac's paper, but it said, So finally, we'd like to mention that Dirac, in a recent published work, that's the famous one, also treats the problem from the same starting point. Both theories seem to be equivalent, apart from the complete difference in methods and equations. However, that precise connection is unclear to us, and he goes on to actually critique the Dirac equation as not being applicable to multi-electron atoms. He does the fine structure calculation in here too, and somehow gets the right answer, even though he's doing multiples of Dirac fermions. So he's dividing by 4 somewhere. I couldn't figure out where. But anyway, so that was Landau's. Well, this is one of the Landau's papers that was lost. I mean, it has like 30 citations from 1927. I didn't know about it just until a couple of years ago. So it was rediscovered by Kähler in '62. It's a mathematician, and again by lattice gauge theorists in the early '80s, who then decided it wasn't as useful as they thought it would be, and staggered fermions was better, and so it was forgotten again. So there's a sort of an interesting history to all of this. So what is it exactly? So it's just an alternative solution to the problem that Dirac was facing, which he wanted to square root the Klein-Gordon operator, right? And so we want some operator K, basically, which squares to give you something like box, right? So you can do that if you write it in terms of the exterior derivative as adjoint, because these are nilpotent. So when I square this, I get d dagger plus d dagger d, which is the Hodge Laplacian, right? So I can write an equation like that formally down, but clearly this phi is not sort of a scalar or a spin one object anymore. It has to be a set of forms, right? Because this equation is only closed if I include all the forms from 0 to d in d dimensions, right? So I can write this equation down. It squares to something like the Klein-Gordon equation. It involves a set of Grassmann-valued p forms, right? And in flat space, at least, it's easy to form a connection back to Dirac. If I take those forms and expand this matrix object psi on the left on products of gamma matrices indexed by the same indices, you can show, it's very straightforward to show that this actually satisfies the usual Dirac equation. So in flat space, these two things are equivalent, but this is a Dirac equation for each column of psi. So I make this matrix fermion out of my forms by contracting with products of gammas, Clifford algebra basically. You can show that satisfies the usual Dirac, and each column of psi is a degenerate fermion. So it describes more than one fermion. It describes 2 to the d over 2 in d space-time dimensions. So it's not minimal in that sense. It describes more than one fermion. But otherwise, it's equivalent in flat space to Dirac. One of the nice things about it is that if I go to curve space, the equation doesn't change at all. Right? So there's a metric dependence buried inside of the dagger here, but there's no need for spin connections, spin structure, field binds, any of that stuff that you need to put Dirac on a curved manifold. There's no restriction for Kähler Dirac. Any smooth manifold, any triangular manifold is actually good enough. Right? So what we've seen is locally in flat space, it boils down to multiples of degenerate Dirac fermions. But on a curved space, it certainly is not. And you can see that explicitly because the Kähler Dirac equation has 0 modes on a sphere, which is certainly not true for the Dirac equation. So on a curved background, there are some sort of corrections to the spectrum of the Dirac theory, which presumably go like the wavelength of the excitation divided by the radius of curvature. Something like that. All right, so locally they look like Dirac, globally they're not. That's where some of the interesting anomalies come from, yeah?
Sorry, what happens to the number of degrees of freedom when you have odd dimensions?
Odd dimensions can be handled too. It's a bit more subtle, so I didn't want to get into it here, but that's a great question. And maybe you should chat later because it would take me a little bit of time to explain. They can be formulated in even and odd dimensions. It's simplest in even. And that's where the anomaly will lie, so we'll stay with that for the moment. But I'm happy to chat later. We have looked at odd dimensions as well. Interesting story.
These things don't have a gravitational magnetic moment.
They have a gravitational anomaly, which I'll tell you about, but this not quite sure.
But they don't have the usual coupling.
Yes, it's a different coupling to gravity. Right. Right. That's important. So in flat space they're equivalent, in curved space they are not equivalent. So far, yeah. Just check I missed something there again. So I can get these things from an action, of course. The obvious thing If I use this matrix version of the story, which I might refer to later, I can rewrite this in terms of this matrix fermion coupled through the ordinary Dirac operator. What's important actually about this is that there's a very simple operator, gamma, which anti-commutes with the Kähler-Dirac operator, the K, the D minus D dagger. And all it does is it takes a form and it flips its sign according to whether it's even or odd. Right, so it's a very simple action, right? But I can imagine exponentiating it to get a U1 symmetry, right? So I can take this field, this Kähler-Dirac field, and multiply it by this phase where this capital gamma sits up here. This is an exact symmetry of the massless action in the continuum. If you ask, well, how do I pick up the even and odd forms? What I have to do is basically sandwich a gamma 5 left and right out in the matrix. When I pull the gamma 5 through, it will either anti-commute or commute with products of gammas. We'll pick out the relevant even or odd forms. So that's how gamma acts in this. And so you can sort of see why that is. If I think about this multiplicative Dirac fermions, of course, it's the Lorentz invariant, but I could also do flavor rotations on it too. And those are separate symmetries. But when I want to talk about these forms, those symmetries get locked together. So the Lorentz group and the flavor group are locked automatically in the Kähler-Dirac picture. And that's going to be important. That's how I get this action out for the forms. So in flat space, the sort of symmetries are very enhanced to those of a multiple of Dirac fermions. On a curved space where you have to stick to the Kähler-Dirac picture, they are locked together, Lorentz and flavor symmetry. If there was if there were a lot of lattice gate theorists in the audience, this would sound very familiar. It would sound like staggered fermions, and that's because it's completely connected to that. So let me. All right, so this has all been in the continuum so far, but I told you that these things have nice properties under discretization, which is why I'm interested in them as a lattice guy. So if I want to formulate this on some sort of curved space, I can always use a triangulation. I could use some genuine, any cellular decomposition would be fine actually, but let's just think of triangulations just for it to be concrete. So I build triangulations in 2 dimensions out of triangles. I just glue them along their faces, along their edges. So I have points and links in triangles. Those are in general called p-simplices. So 0 simplex is a point, 1 simplex is a link, 2 simplex is a triangle. I specify them by listing their vertices from 0 to p. So there are p plus 1 vertices in a p-simplex. Once I orient these p-simplices, so a link has a certain direction, then I can invoke what's called the boundary operator delta, which acts on this list of vertices specifying the p-simplex. And it basically just deletes the vertex. So it gives you one of the faces. Right? So this is standard discrete calculus, stereo calculus. So I just delete. So if I want to take a triangle, I can delete one point that will give me this particular boundary, or the other boundary, or the other boundary, right? So I can get, for example, a triangle gives rise to 3 different faces, the links on its boundary, right? And they come in with a sign which reflects that orientation, right? So for example, if I act on the triangle 1, 2, 3, I delete the first guy, I get 2, 3, that's a link 2, 3. Or I delete the second guy, I get 1, 3 with the minus sign here, or 1, 2. And then with the definition of 1, 3 is plus is minus 3, 1, I can write this. So I just get so for example, the boundary operator acting on that triangle, the 1, 2, 3 triangle gives me 2, 3, 3, 1, 1, 2. It gives it the oriented boundary. None of this is new or anything. It's just standard stuff. So in an orientable triangulation, you can arrange it so each face is carried with opposite orientation, the 2 neighboring simplices that are glued together along that face. So that's the sort of geometric structure I'm going to use as a background. If I want to know how to put a theory of forms on that background, I simply map these p forms into what are called p cochains. That's fancy language to say I put a field on every p simplex. So I have fields on points, fields on links, and fields on triangles, right? That's what I mean by this. And the way the boundary operator acts on that field is it gives me the fields on the boundary components, right? Through this incidence matrix I here. So this is 0 unless p minus 1 lies in the boundary of C of p, then it's either plus or minus 1 according to orientation. So I can make this thing act on these p cochains, which are going to be the analog of lattice p fields, if you want. And so there's also a co-boundary operator, which sort of does the opposite thing, the transpose thing, that tells me, it gives me something non-zero here when C of P lays in the boundary of C of P plus 1. Right? This is basically the adjoint of this guy. Right? It's not hard to verify that these are nilpotent, just like the exterior derivative.
So far, you've not shown the metric.
Sorry?
So far, you've not shown the metric.
No, I'm just as, if I wanted to put in the dual lattice to actually write down the metric parameters on the lattice, I would have to do that. I'm setting all those to 1 at the moment for simplicity. It doesn't affect the basic discussion. You're right. So these are just zeros and ones everywhere. I've thrown the lattice spacing away and I don't have explicitly rescale all the fields by all the dual parameters. Let's assume for simplicity, let's assume all the triangles are equilateral or all that, right? So all of that is just a constant. Check and absorb. All right, so these are the basic elements that we need to write down the Catterall equation on a lattice. And what it looks like is just this. So I replace D and D dagger by these boundary and co-boundary operators. They act on a set of P cochain now, but it's just really a set of lattice fields on the simplices. And I get the Laplacian by squaring it, because these are nilpotent, it's the same thing. And if you do this on a simple, say, two-dimensional triangulation, you'll recognize the usual discrete Laplacian you know and love. What's really key about this is that the zero modes of this match those of this. So the continuum Taylor-Dirac operator has precisely the same zero modes as the lattice version of the story. Right? In fact, they're just given by the ranks of the homology groups. So the zero mode structure is completely preserved by the discretization. That's key. Right? So that's going to be at the heart of why you can match the anomaly. In addition, there's no fermion doubling in this. So unlike with the usual Dirac equation, when I double, I have to get left and right-handed species. That's not true here. So if these zero modes have a particular sort of chirality, they don't get doubled up anymore when I laticize it. Right. So in other words, the continuum limit describes 2 to the d over 2 Dirac fermions. So it's not 0, it's not 1 fermion, but it never was in the continuum either. There's no additional doublers that come up under discretization. The spectrum goes smoothly into the continuum spectrum with no additional states. It's obvious that gamma still anti-commutes with the lattice version of K, because it's such a trivial operation, it just flips the sign depending on what's even or odd. So this U1 remains in exact symmetry too. And I can play this game on any triangulation with any topology. It's very straightforward. We've even done simulations of this thing, so it's completely concrete. There's probably no one in this audience that actually cares about this, but if you've ever heard of staggered fermions, they're a way of doing lattice QCD, and also a rather old-fashioned way of doing it. They're just this Taylor-Dirac guy restricted to a regular lattice. So if I forget about triangulations, go to a regular cubic lattice, talk about p-cell decompositions instead. All the technology works the same way. These forms that we talked about really just correspond to the staggered fermions. What happens is you have to draw a picture here. Just draw a picture in 2 dimensions. So here's my starting lattice. So I might have a scalar form here. I might have a 1 form here, maybe another 1 form here, and then a 2 form on the plaquette. So I'll put it at the center. So that's my initial set of forms. But clearly I can simply draw a lattice with half the lattice spacing, and these become psi, psi2, psi1, and psi1, 2, which were originally forms, and now just like side fields on the finer lattice. That's what you do to map it into staggered fermions. So I can map, so that's what's happening here. So I'm introducing a lattice with half the lattice spacing, and then according to these indices here, I just map to a single side field. You can build a matrix fermion out of the staggered fields, just like you did in the continuum with products of gamma matrices. You can actually plug it into this discrete version of the Taylor-Dirac action. And what you come up with is this object here, which is the staggered fermion action. If you don't care about staggered fermions, you can switch off, but that's very recognizable to a lattice person, because that's one way of discretizing the Dirac equation. These are 1 component objects. This is the symmetric difference operator. This is a set of phases, which are given by this formula here. The fact these are plus minus 1 comes from the fact you had exterior derivatives, so anti-symmetrized derivatives. So that's where the phases in staggered fermions are coming from.
It gives you that eta, precisely that eta, not some gauge equivalent.
You get precisely that eta with this definition, but you don't have to use this. You can do a unitary transformation which is different from this one, and you'll get a different set of etas. So there's a close connection between the Catterall equation and these staggered fermions when you go to flat space. Another way of saying that is the Catterall fermions you could think of as a generalization of staggered fermions to arbitrary curved discrete spaces. That's another way of saying it. This gamma operator that we talked about is just the site parity of the staggered fermions. So again, that may not mean much to you, but it's important for lattice people to recognize where this is coming from. So what this Catterall thing is basically not unconnected to something rather well known in lattice QCD edge. These types of fermion discretizations are well known. The reason that none of the interesting anomaly structure was discovered early in the days is the anomaly vanishes on a flat space. So you won't see it. I'll show it in a moment, but you won't see it if you just formulate the theory on a flat space. So the Catterall is just a geometrical or beautiful way of formulating staggered fermions. So let me show you this anomaly. So I'm going to set the mass to 0. It has to be massless fermions. I'm going to work on some finite triangulation with, say, a spherical topology. So I'm going to compactify my d-dimensional space onto a sphere. Right? Under this U1 symmetry I talked about, it's trivially obvious that the action's invariant. Even the discrete Catterall action is just invariant under that U1. But the measure is just not invariant. So if I think about the fermion measure, it's a product of all the p simplices in the lattice. Right? There's a phi and a phi bar to do for both. There's an integral over both of them to do. So let me pick the points, for example. The points transform like e to the 2I alpha, if I do a right, times the number of points. And I go to the links. I get e to the minus 2I n1, the number of links, times alpha, because links have minus 1 to the p is minus 1. Then I do the triangles and set it all the way up. So what you notice is I get the alternating sum of the number of simplices of a given type. So points, lengths, triangles, etc., all the way up to d. In other words, the measure here for these fermions transforms by a pure phase, which depends on the Euler characteristic. So if I formulate this theory on different topologies, it's explicitly not true that the measure is invariant under the U1. It's explicitly broken in general for chi, as long as chi is not 0, right? So on a torus, it's actually invariant, but no other topology is that true. So the U1 is actually broken. The anomalous piece is Z4, right? Because of the factor of 2 here, right? And the fact that chi is equal to 2 on the sphere. So this is an example of an anomaly of a fermion system with a local operator, all on site, with a finite number of degrees of freedom. So although the action is invariant, the measure simply isn't, and you don't. So this idea that you need an infinite number of degrees of freedom to capture anomalies is not necessarily true. This is a counterexample to that. In fact, there's an index theorem for this. It says the number of zero modes of my Taylor-Dirac operator with plus gamma chirality minus that with negative is equal to chi. So this, you can do this calculation in the continuum too. You can, and a la Fujikawa, you'll get the same answer. The calculation on the lattice is trivial. It's just counting.
Is interior reflection positive?
Good question. I think, well, on a random, I don't even know how to define reflection positivity on a random triangulation. I don't know.
You can take one that respects a kind of invariant symmetry of the sphere, let's say. All you need is to be able to cut your sphere in half.
So you want.
Well, the reason I'm asking is that the way that the Euler character shows up in the anomaly is the way that's kind of backward from what we're used to in the continuum.
You mean that? Well, this chi, of course, is the Riemann. Is a different contraction Riemann than normal guy that would give a gravitational anomaly.
So normally the Euler anomaly appears in like the trace anomaly and not with the
Yes.
chiral
Right.
anomaly.
Right.
There's a difference of an I.
You're worrying about the I,
That's what I'm asking about reflection positivity.
because you have two epsilons in the continuum.
So normally every I, reflection positivity says every I goes with one epsilon,
Yeah, and now you have two epsilons.
or none if you wish.
Well, I can simulate this theory. It's not sick in any way.
No, the Euclidean theory is not necessary.
Yeah, I think that, so you're really asking about
Just kind of asking about.
CPT, really.
Yeah. Exactly.
Yeah,
Euclidean CPT.
well,
Which is reflection.
I don't know how to define the reflection operation, but this is a perfectly good symmetry of the action, and it's perfectly not a good symmetry of the measure. And you're worrying it should be a real phase, not really a phase, it's just either the I alpha carrier.
Indeed, that's what you would expect for an Euler character.
I have to think about it. I'm not sure. I think it's okay, but I don't.
I'm not saying.
I mean, we've been thinking a little bit about how to formulate this in Hamiltonian terms, so this is maybe something that we're going to be, I'll say a little bit at the end about that. It might be relevant. This is purely Euclidean at the moment. I'm just wondering whether you could remove the I and keep most of the stuff. I mean, your connection to chiral symmetry would be. All right, let's come back to that maybe towards the end. All right, so the true symmetry is actually Z4, not one, U1, at least there is. So what happens if I imagine gauging it? I'm thinking about Toft anomalies now. So a typical term in the action couples my lattice phi bar to my lattice phi on a p-1 simplex through this incidence matrix. So if I do a local Z4 on these fields, I have to promote this guy into a gauge field. It's the usual story. So I can gauge this in the way I would gauge any lattice theory by inserting an appropriate Z4 gauge field between the different simplices that occur in the action, right? So there's no barrier at that level to gauging the action under Z4. However, the measure involves only a d phi and a d phi bar. This is not invariant under local Z4s. It actually changes by a sign in general, all right? So the only way I can make the measure locally invariant under gauging the Z4 is that if I have two copies of my system, right? Because then the minus signs cancel out. So in general, the measure, if I try to gauge the Z4, so I'm thinking about Z4 Toft anomalies, I can only do that if the number of flavors of my system comes in multiples of 2, right? Because then the measure is actually locally invariant too, as well as the action, right? Does that make sense? So there's a very simple mod 2 anomaly in this system too. Just coming from the measure, again, coming from the measure. Yeah. So it's kind of, so it's a good time to pause and see where we get back to.
Just ask a quick.
Yeah.
What if you are on a surface with vanishing Euler character and then you try to gauge the full U1?
I think there's no immediate barrier to doing it on just living on the torus. I don't see a problem. I think you'd have the full U1 on a torus.
And no intrinsic Toft anomaly for that U1.
No, I don't think so. Well, no. Actually, no, I'm not sure you. No, I think you wouldn't be able to do it there either. The measure would still be problematic. Yeah.
That sounds better, yeah.
Yeah, that's right. So let me summarize what I've said so far. So these Dirac fermions we've been playing with generalize these staggered fermions to curved space. They have this exact U1 symmetry. There's no doubling because the generator of the U1 is not the usual gamma 5, it's this twisted gamma 5. On a sphere, it breaks to Z4, and that's a natural compactification of flat space. There is this additional Toft anomaly associated with trying to gauge the Z4. To cancel that, I need even numbers of these Dirac fields. So let's think about what that counting means in this case, this thing in particular, the fact that I need even numbers of Dirac fields. So in flat space, the system that I told you, one fermion gave you 2 to the d over 2 spinors. So it's 2 to the d over 2 plus 1 now because of even. So if I plug in, or 2 to the d over 2 plus 2 for Majorana, if I have real reps, right? If I plug in d equals 4, for example, that's 4 over 2, that's 2. So that's 2 to the 4. So that's 16 Majorana fermions, or 16 Weyl fermions. If I do it in 2 dimensions, this is 1 plus 2, so that's 8. So that's 8 Majorana fermions. These are the magic numbers that condensed matter guys know cancel out, allow for gapping in topological superconductors, for boundary states of topological superconductors. You can also get these numbers by trying to cancel off various Toft anomalies associated with time reversal for Weyl fermions and spin Z4 symmetry in this case. So depending on the dimension, so maybe I'll skip to the end and just show you that table here. So in different numbers of dimensions, there are different types of discrete symmetry I can care about for ordinary Weyl fermions or for Majorana fermions. And they predict certain numbers of fermions are needed to cancel those Toft anomalies. And they're all predicted by the same number of Kähler-Dirac fields. This R means reduced, so it's twice what I told you. I said 2 so far, but these carry half the degrees of freedom, and I'll get to this in a moment. So it's the same. So it's the counting in all dimensions coming from this gravitational anomaly gives me all of these special numbers I get from different types of symmetry for spinors. So it seems that the lattice knows about these things in a kind of very kind of nice way. Okay. So, all right.
Sorry,
Yes.
can you explain why there's a problem with ABJ visualize?
Why? You mean for gamma 5?
Yeah, like you wanted to cancel this ABJ anomaly for like, let's say chi equals to 2 by restricting U1 to Z4. Or like
So let me go back. So to somewhere here. So you start this U1 symmetry. If you're living on the sphere, the real symmetry is only Z4.
But like that is non-anomalous.
That's non-anomalous.
But what is wrong with
There's nothing wrong with that. But if I want to understand the Toft anomaly structure, then I have to imagine gauging that Z4. That's a separate step beyond that. Okay, and that gives me constraints on the long distance non-perturbative structure of the theory in general.
But in this case, like when we didn't for usual.
There's nothing wrong with this theory by itself. It just has a Z4 symmetry, not a U1.
Yeah, but when we do this scalar fermion, like we have a finite dimensional Hilbert space, and so there's no way to have this like there's no explanation like about the ABJ anomaly. But now we have this like.
I mean, strictly, of course, it's not ABJ, it's ABG-like, right? But just make sure, right? It's just it's a breaking of the U1 down to Z4 in this particular theory.
But in this case, we have like infinite dimensional Hilbert space, so we don't. Like,
in this case, we only have a finite dimensional Hilbert space. If I do this,
but like you had a degenerate like P form.
I had 2 zero modes, right, associated with the fact that chi was 2. Not sure I understand the question.
Sorry, maybe I misunderstood that. Yeah, I thought usually on the lattice you don't have ABJ anomaly, or in the continuum you have the ABJ anomaly because you have infinite dimensional
Yes.
space.
So this is an example where that's just not true. I can make this work in 2 dimensions with the crudest tessellation of the sphere that is a tetrahedron. That's already enough to capture the anomaly. So it's completely topological.
And I try to understand this because.
So I think the difference is the topology you can capture with the lattice is actually the space-time topology, right? That's what chi is giving you. Whereas normally you're worrying about the topology of the gauge fields. And that's what you need an infinite number of degrees of freedom to capture. So ironically, it's easier to capture the topology of space-time in some sense. The lattice is more happy with that than it is with the gauge field topology. Maybe that's it. Is that better?
Yeah.
Okay, so I told you that what I've said is very interesting, perhaps, but has nothing to do with chiral fermions yet. So let me say, because this is not gamma 5 we're talking about. So the question is, what is the connection to chiral fermions? So I have one more thing to tell you before I do that, which is I have to tell you about these reduced Kähler-Dirac fermions. So we started with this full Kähler-Dirac action, but because gamma anti-commutes with K, that action decomposes into 2 parts. This is like decomposing Dirac into 2 Weyl, right? Because this minus and plus, they don't the eigenvalue of gamma, right? So it always K couples minus the plus and etc. Right? If I just drop one of those terms, I get what's called the reduced Catterall equation. It's like dropping one of my vials in Dirac to get with a single quotes left-handed field, say. It's the analog of that, right? So this curly K just represents that. These projectors are nice local projectors, just like in the continuum. You can do this. These things are naturally massless because this vanishes by projector, this vanishes by Grassmann. So these are naturally massless fields that will come out of this projection. And I can do this on the lattice just as much as the continuum. If I go to staggered fermions, it's equivalent to what are called reduced staggered fermions, which are not much used in QCD because they usually have sign problems, but they're well known, or at least were well known in the 80s at least. So in this case, this Z4 anomaly I told you about, Toft anomaly, is cancelled for 4 copies, not 1, not 2 copies. I work in terms of reduced fields, which is what I want to do. Okay. So let me give you the first hint that this is interesting. Suppose I go to take my matrix form of the Dirac field, Taylor Dirac field, say psi plus. This is a reduced guy, right? And I go to chiral basis, for simplicity. It's easy to see that this matrix is 3 plus 1 here. This matrix psi has actually this block structure. Right? It has half the number of degrees of freedom in the full matrix. So what happens is in chiral basis, those are zeros. In other words, I have a doublet of right-handed fermions and a doublet of left-handed fermions. Right? There's two independent SU2 flavor symmetries that act in the naive continuum way. This is continuum. Right? I can't write Majorana mass terms for either of these down because it's SU2. If I try to couple them, I'll break the flavor symmetry. So this thing doesn't have any, if I imagine gauging that flavor symmetry, there's no gauge invariant mass term I can write down to this. It's a chiral theory. So although I didn't start out going after gamma 5, these reduced Taylor-Dirac fermions are very closely related to certain classes of chiral gauge theory, certain classes of chiral theory. Remember, I needed 4 copies of this reduced fermion to cancel out the gravitation, the Toft anomaly. That means that this theory also has, these guys have indices running from 1 to 4, and there's another SU4. Right? So there's fermions that live in the formal continuum limit, live in a 4-2-1 plus a 4-bar-1-2. These are the flavor symmetries that come out of the matrix structure, and this is just the additional 4 I had to put in to cancel out the Toft anomaly. Right? These are the matter representations of Pari Salam, and this is it. So it's not true that these connect to regular chiral gauge theories, anyone's chiral gauge theory, but it does seem to select out at least a class of these theories in the formal continuum one, as long as I use the reduced fermion. And so, what time is it? Got a few more minutes. Nearly, I'm not too far off the end. So the question then is, suppose I replace my Taylor-Dirac fields by staggered fields, these standard lattice fields. Is how much tuning of that lattice theory would I need to target Pari Salam in the continuum limit? Okay. So the problem is in this flavor sector. The SU4 is easy to gauge. We know how to gauge that. 4 copies of staggered fermions, it's trivial. This is not trivial though, because this is broken by the lattice. This structure, this SU2 cross SU2 structure is broken when you laticize the theory. However, the staggered fermion theory is invariant into what are called shift symmetries. So I can take this staggered fermion and I can move it to a neighboring site with some phase. These are well known in staggered fermions, but this phase is related to the etas that I had before. And in fact, these shifts compound together. So for example, I can do a shift in the mu direction and a shift in the nu direction. That gives me another generator S mu nu, another symmetry of the theory. In fact, they satisfy an algebra, which roughly speaking says is identical to the algebra, the Clifford algebra itself, up to a translation on the block lattice. So it mixes translations with these shifts close on a mixture of translations and shifts. The existence of these symmetries in the massless theory stops you writing down mass terms, just like in the same way that this symmetry would stop you writing down mass terms too in the continuum. In fact, these shift symmetries are related to a sort of a subgroup of this, a discrete subgroup of this continuum symmetry. If I had more time, I would spend some more time on this. You could give a whole seminar on this, but so the point is that this staggered fermion theory, which is really just discrete Catterall on a torus, has an existing symmetries which move you on the fine lattice, right? The block lattice is the physical lattice. The fine lattice is where you're putting your degrees of your fermion degrees of freedom are being put on the fine lattice. Okay. So fix this next time. All right, we'll get there. So it's known, though, that as far as global symmetries go, the existence of these symmetries as a discrete subgroup guarantees the restoration of the global SU2 plus SU3. So this is what's called taste restoration in lattice gauge theory. So the existence of shift symmetries guarantees that the continuum flavor symmetry is automatically restored for an asymptotically free theory as you take A to 0, the lattice spacing to 0. So there is some hope that this symmetry can be restored, but it's one thing to say I can restore it as a global symmetry. It's another thing to say I want it to be a gauge symmetry. And that means I need to gauge some of this subgroup. I need to be able to gauge these shift symmetries in order to have a hope of having an emergent gauge symmetry like this. So that's really kind of where we are right now in terms of trying to figure this out. My student and I did a little bit of work in this direction last year, and it's not completely hopeless. So these shifts that we were trying to do here actually come up along with a parameter alpha, which lies in Z2. So I can change the sign here. So there's in some sense a Z2 piece of the shift symmetry I can try to gauge. But it's so if I do that, if I look at one of the terms in my action, which couples x to x plus nu, this is just some hopping term. When I do it, one of these local shifts, I'm going to make the alpha now be a function of x, not just be a global side. It will pick up a phase factor like this. So the hopping term will pick up something like this. And if you look at the surface for a moment, you realize that I could actually imagine this looks like a gauge transformation of a plaquette-based Z2 gauge field. So if I had a gauge field situated on plaquettes, it transforms by its boundaries, just like a link transforms by its boundaries. So this is a discrete two-form gauge field. I can arrange it so that its gauge transformation cancels off these extra factors of alpha coming from the shift, the local shift. So if I dress the fermion link with plaquettes around it and make sure they transform this way at the same time as I do this shift, I can render the fermion action invariant under this Z2. So this is just a discrete subgroup of the thing you want, but at least I can implement it in a concrete way on the lattice. So I have a discrete, strange kind of gauge symmetry, which involves shifting the fermions by one side. And the only way I can do it is using these higher form gauge fields on the lattice. So they're abelian, of course. And I can make this work for the higher shifts too with higher form lattice gauge fields. So this is just a brief idea that maybe there is some way if we can try to actually gauge this discrete subgroup, and hence hope we get a gauged SU2 cross SU2 in the continuum line. And there's a lot of ifs there, because first of all, you have to look for phase transitions in the lattice theory, where I can take a continuum limit. So now I have additional higher form gauge fields that I have to worry about, and I have to try to tune them in order to take a continuum limit. And then you have to ask the question, well, what do I get out in the continuum limit? Is it a gauge version of SU2 cross SU2, or is it just something else? It just remains Z2 cross Z2. And so in some sense, you're gauging a Z2 piece in both of these. So I'd say this is very much kind of up for grabs at the moment. Yeah.
This bilinear, why isn't it shifting by mu in the argument?
By
The chi x.
well, it does, but then you can always shift the summation over x back by that.
Oh,
So the way you show the way you do the transformation is you have a sum over x, right? So what happens is this gets shoved by mu as well.
Oh, I see.
But then you can transform x prime as x minus mu and get rid of those factors, but then you pick up these factors. So, yeah. One slide on Hamiltonian perspective. I can take these chi's Now I'm just thinking about a spatial slice only and decompose them into two real fields, and I can write a Hamiltonian for my staggered fermions, which looks like this, where these guys anti-commute. These are the analog of Majorana fields, right? So they're square to 1, or anti-commute to 0. The Hamiltonian is invariant under obviously a phase rotation, right? An SO2 rotation on the lambdas, which rotates these two lambdas into each other. These shift symmetries I told you about, and also time reversal, which acts on them in a particular way. It's possible to show that time reversal commutes with the shifts, and M commutes with the shifts, but M doesn't commute with time reversal. So in the Hamiltonian picture, I can't, for example, gauge this SO2 symmetry, this vector symmetry, at all, without breaking time reversal. So there's a 't Hooft anomaly associated with that. If I break, so suppose I break my U1, my SO2 down to Z4 by adding, say, 4 fermion terms, then the only thing I have to worry about is not M, but just R. This matrix R, this is up here, is the R to the 4th is 1. So R is my Z4 generator. This thing anti-commutes with T. And so if I have copies, if I can build a theory in the Hamiltonian picture, which is actually invariant under for which the total R commutes to the total tau and acts on all the fermions, providing I use multiples of 4. So I can reconstruct that Z4 anomaly, that 't Hooft anomaly, in a Hamiltonian picture using these arguments. This is very schematic because I'm out of time. I'd say it's fair to say we're starting to think about how the Hamiltonian formulation and exactly how it connects back to this Z4 anomaly. And that might address some of the things you were asking about reflection positivity, or in this case, CPT invariance.
Yeah, I was thinking about it more. It seems the structure of the anomaly that is very similar to the structure of the chiral anomaly that, for example, appears in Benton's twisted n equals 2 theory, which is not reflection positive.
Right.
So we do something very similar. So what he did is he took a fermion that also transforms under an SU2 flavor symmetry, and then identified the SU2 flavor with, say, a chiral part of the SU2 of the Lorentz group. Then you get forms.
Sure. Yeah. No. This twisting business goes.
In that case, the phase anomaly, the standard chiral phase anomaly, turns into something that can have an Euler character on the right-hand side, because when you identify the spin connection with the SU2 background field, the instance anomaly can spit out.
Yeah.
But I think it requires you to violate, some version of spin statistics or reflection positivity in curved space.
I mean, it's certainly true that this Taylor-Dirac business is closely connected to topological twisting that Witten did, back in the 80s.
Yeah, so let me actually follow up.
It's like the n equals 4 theory can be twisted.
So 4D, for example, you have an SO, you have a Dirac fermion that also has an SO4 flavor symmetry simultaneously, right?
Yeah.
And then you diagonally.
Yes, it's the diagonal subgroup of the flavor and the Lorentz group that you're focusing on when you talk about Taylor-Dirac. That's right.
Yeah, so I think whenever you do that, so in the Euclidean,
you might mess with the reflection positivity.
Yeah, because in the Euclidean setting, both of them are SO4s, but the Lorentzian setting, one is not. So
there was a story there? I'm trying to remember now. And maybe we should talk later. Yeah. Okay. Good. So let me just summarize anyway. So this Taylor-Dirac business might represent an alternative path to at least a particular class of chiral lattice gauge series, at least in Euclidean formulations. It's not constrained by Nielsen-Uyemiya. The relevant symmetry is not gamma phi, but this funny twisted chiral symmetry. The anomaly structure survives discretization, so it certainly is a counterexample to the folklore. You can't make quantum mechanical theories exhibit simple anomalies unless you do exotic things with the symmetries. These are on-site, local symmetries. It's closely connected to staggered fermions, which is numerically important, if nothing else. And the minimal anomaly-free model of the reduced version of the story looks like it targets Paddy's Salam. And the question is, can you take this piece and try to do some appropriate gauging to try to get directly to something which looks like Paddy's Salam? And that's not easy, but I showed you sort of the directions we're thinking about right now. That would mean you had emergent SU2 cross SU2 gauge symmetry for this to work. That would help. That would help. Okay, thanks. Sorry.
Actually, one question maybe made, but
Sure.
I mean, you say talk about the continuum limit different for the Dirac one versus the scalar Dirac in curved space.
In curved space, there would be different.
Yeah. So how would they be? I mean, so especially in the massless case, you don't. You can really add higher derivative terms. You know, scale. It's massless. So what would the difference be? Is it local or something?
Well, I mean, as I say, I think the corrections would go like something like the wavelength of the excitation over the radius of curvature. The radius of curvature is finite in the limit you're interested in still, right? So the spectrum would be deformed, you know.
I'm just trying to imagine sort of some effect of Lagrange and what those terms would.
Yeah, I don't know. It's actually very interesting to ask this question because you can say, look, these scalar direct fermions are maybe a nice scaffolding to erect a lattice theory around. But you can say, you know, how do we know the world isn't actually built out of scalar direct fermions? How do we actually know what the difference is? You know, modulo all the mass breakings and things. You could ask, perhaps, you know, at a fundamental level, the Planck scale or something like that. The world is populated by scalar direct fermions. After all, we know the standard model is not one direct fermion. It's 15, or arguably most people would say 16 via fermions, right? Which is the minimal package you get here. So you could actually ask, well, how would I know? How would I see in a scattering experiment, or if I looked at the Huh?
Isn't the stress tensor of these guys zero?
No, that's I think only if you think of them as ingredients of a topological theory. I don't think it's just no. So there's a metric dependence because D dagger has a G dependence in it. It's not like the Caylor-Dirac operator doesn't know about G. Through its adjoint, it does. So there is a non-zero team unit.
That's true, yeah, but it's different than.
It's different from the Dirac. So there will be corrections if you looked at scattering of neutrinos from the early universe or looked at neutron stars, equation of state, you should be able to see a difference.
Here, if you get movement between two gravitating bodies. The
Uh,
stress
why
tensor
would you
might not be zero, but it's not the same as in.
Well, in any region of flat space-time, it's going to look like the Dirac fermions.
No, but the stress tensor will not be the same.
Right, but the correction, I don't.
Even at the linearized order, the theory is different. From the moment you go away from flat space, the theory is different.
Yeah.
Even at zeroth order, the stress tensor is different.
True. Should be, well, I think you should be able to.
Because the discussion we just had about twisting means that one way to think about these is to start with a mono Dirac fermion and replace the background gauge field that couples to the Dirac fermion by the spin connection.
Sure, yeah, right. If you do that here, by the way, we actually did that continuum calculation, you can take the Caylor-Dirac theory, you can write it in terms of spinors and a spin connection. It's just that the way the covariant derivative acts is different from what on a Dirac fermion. Instead of being omega times psi, it's more like the commutator omega with psi because of the diagonal subgroup structure of this.
Right, so that means that even the like tree-level graviton vertex is different.
Yes, I think that's right.
So even one graviton exchange will be different. So something to check.
Yes, no, I think there are interesting things questions that have nothing to do with the lattice that you would check.
Yeah.
And you say, what are the experimental bounds on this? How would I know for certain that this is not the way things are?
Does it even satisfy the equivalence principle?
Why would it not?
What does a gauge filter about it?
Well, because the gauge, so the equivalence principle is the statement that the metric is locally flat, but there's a place where you also substitute the spin connection for some gauge field.
Yeah, so there's an additional gauge.
Yeah, there's an additional coupling, and that doesn't obviously satisfy the equivalence.
Yeah, true. Yeah.
But that's an easy thing to check.
Right. So I think in flat space, there's no problem. Because in flat space, I just have an complete equivalence.
Yeah, as long as you don't couple the gravity study correlation.
So I couple the gravity to get my anomaly structure, then I take the radius of curvature to infinity. So I'm back in flat space to do my gut theory.
As long as you don't want dynamical gravity. In
Yeah.
space.
Right. Yeah, I mean, in that sense, you could think of the original anomaly as kind of like a tough anomaly. What happens if I curve the background? It's like if I switch on a background gravitational field, what happens to the fermion measure? Right. So it's now then it breaks. That is like a mixed tough anomaly, breaks the U1 down to C4, and
That's true, but the thing that I was complaining about before is that normally in that computation you would get the signature of the network, like the Euler.
Yes, and it isn't that. No. So this question of reflection positivity, it's a question of how many factors of I. You get an I with any epsilon. That's the normal
That's the
story.
usual.
Is that cast iron? I mean, what causes that? Because it seems to be in some sense the flavor space, which is where one of the epsilons is coming from, and the other one, the Lorentz space, are
So
at least in flat space, they start to decouple. Right? I'm forced to tie them together.
but you're forced to tie them together on the curved space.
Yeah, that's
the
true.
point. And so the flavor indices kind of like act like
Yeah.
space-time indices.
Yeah.
Yeah, I agree with you. If you can, if you write them as separate epsilon, then you treat the indices
You
separately.
can do what you want.
It's fine. And I think this.
Okay.
I think it's just the descends from the usual chiral flavor anomaly. After you plug in the spin connection for the flavor background.
Mhm.
That's my vague recollection.
Yeah. Yeah. So I don't, in the Euclidean theory, I'm still not sure there's necessarily a problem.
Well, it depends what.
I mean, if I write a path integral to represent some amplitude in the Minkowski theory in terms of Euclidean path integral, I'm allowed to play games though in terms of.
Well, if you're trying to describe it.
I don't know how to define reflection positivity in general once I curve my space. I just don't know how to do it operationally. Because I have some random lattice and what it even means. So I don't have T. This is so. I guess what you need is a path back to Minkowski space where you have a CPT invariant theory, which somehow retains the kind of conclusions you're getting from this Euclidean theory.
I think it's
In terms of like the number of fermions you need, for example, to cancel out the enormous.
Yeah.
That's something concrete.
probably something completely different. I want you to actually add a little to that.
I mean, maybe we should.
Yeah, offline.
Yeah, let's just
All
offline.
right, let's thank Simon again.
Yeah. That was a very nice talk.
Sorry, I don't think we met.
I don't think we met.